Okay, thank you very much for that introduction, and thank you, all the organizers, for inviting me to come and present our study here. I was asked to present a study we did on background ionizing radiation and childhood cancer. But I decided to be a bit broader because there have been a number of other studies which I think are very relevant. And so I would like to summarize other studies together with ours to see what they can tell us, hopefully, about effects of low-dose radiation. So I will briefly give you a background of natural radiation, the different types of sources we have, and then turn over to some the different study designs that have been used to look at this links to childhood cancer. Just to give you some limitations of these different study designs and to hopefully understand what we can learn from them. And the main focus will then be on the recent studies that have been done in the last 3 years, including particularly the study we did in Switzerland. So what do we know about background radiation or ionizing radiation in general and childhood cancers? So what we know comes mainly from, and tragically from, the atomic bombs that were dropped over Japan. And I think with regard to childhood cancer, these are the main 3 lessons that we learned from there, that high acute doses can induce leukemia, and leukemia is the most common cancer in childhood. So childhood cancers are much rarer than adult cancers, and they're also very different in type. So we rarely have any carcinomas. We have a lot of blood cancers, so we have leukemia, we have lymphoma, and we also have many brain tumors. So it is interesting that particularly leukemia can be induced by radiation. What we also learned is that children are particularly susceptible and that there is a short latency for childhood leukemia. So we know this from the observed 15 cases of childhood leukemia in the lifespan study. That doesn't seem like a lot of, in absolute numbers, but in relative terms, we only would expect 1.5. So this is a 10-fold higher number. And if you translate that to a dose response, we have in the order of 50 to 100 excess relative risk. So these are very high relative risks that we're looking at. We know relatively little about what happens at low doses. And this is, of course, the topic of the current session. But if we extract from the models, the risk models that we have from the lifespan study, we assume that we can extrapolate this to low chronic or protracted doses, like for instance from background radiation, then we would expect that quite a number of the cancer cases that we observe in the general population in children would be actually caused by natural background radiation. These estimations have been done in the UK and in France, and they arrive at a number of about 20% of cancer cases that would be due to natural ionizing radiation. So this is quite a large proportion, but there is a lot of uncertainty here. So potentially we can use natural ionizing radiation to learn more about the effects of low dose, but it has also been shown that we would need extremely large studies. So let's look a bit closer about what are the sources of natural ionizing, the natural sources of ionizing radiation that we are all exposed to. And if you look at the worldwide average, so we have here numbers from UNSCEAR, where we see that we have about a 2.5 millisievert, an annual dose of 2.5 millisievert worldwide. So that is a very low dose, but if you think that we accumulate this over our lifetime, we can easily, there's a lot of variation over space, so depending on where we live, we can easily reach doses of several hundred millisievert. The dominant part of this comes from radon, so radon gas that we inhale and that accumulates in our homes. Then there is quite a large proportion from terrestrial gamma radiation coming out of the Earth crust, mainly due to the uranium content in the Earth crust. And then we have a component from cosmic radiation, but also a smaller component that is ingested radionuclides from food and beverages. So judging on this, if we think of what we should be studying, we would think that we should be looking at radon. But we have to be careful because we're dealing with childhood cancers, and if we look at individual organs, the picture may be very different. So this is estimations for the total dose that a child in the UK would receive to the red bone marrow, which is where leukemia originates. And there the picture is very different. So the largest component here is through ingested radionuclides, followed by gamma and cosmic rays. And in fact, the inhaled radon component is a very small component to this dose. This is because inhaled radon the radiation is largely deposited to the lungs and is relevant most importantly for lung cancer, but perhaps to a lesser extent for leukemias. Nevertheless, most of the studies that have looked at natural background radiation and childhood cancers have focused on radon, quite paradoxically. So let me now turn to the studies that have been done prior to the study we did. And you don't need to look at this table in detail. I just want to summarize roughly some of the studies, all of the studies that have been done before. So the first, and I'll begin with radon. So the first thing you can do if you want to study this association is you can do an ecologic study. An ecologic study is where you simply compare different regions with each other. So you look if a region that has a higher on average natural background radiation also is the region with the higher incidence rates for cancer. And there have been many studies that have looked at that for radon. Most of them come from the UK or from the US, and you see here, I can't read the Japanese, but there are very different types of area units that have been looked at. And I've tried to summarize qualitatively the results here with a plus, meaning that they found significant results, positive results of an association. And the plus in parenthesis means that the results were of borderline significance, so not very strong evidence. And then we have other studies here that were either negative or borderline. So you see that most of these studies do seem to find an association. But this kind of study design doesn't have very much credibility in epidemiology, because we don't know whether the association we find between the differences we see between regions actually also reflect true differences between individuals. So whether the individuals that are more highly exposed within a region are also the ones with the higher risk. We don't know from this kind of study. So the next best thing we can do is a case control study. And typically for rare diseases, we would do a case control study where we collect a number of cases through a registry, for instance, and then we sample some representative controls from the population from which these cases came, and we actually try to measure the exposure of all the individuals that in our study, and to see whether the cases have on average higher dose than the controls. So there have been a number of studies that have tried to look at this. These are except for these ones, I will come to these. But these studies here are such classical case control studies where the investigators either sent questionnaires to the individuals to find out where they had lived, the whole history of where they lived, or actually placed dosimeters in their homes to measure their exposure. The problem with these studies is that they're very expensive, and you can only include you can't make very large studies with this kind of design. And you also have the problem that people might drop out because they have to actively participate in the study, and many people are reluctant to do that. So there are many reasons why these studies tend to be biased. You see that the picture of the results here is more heterogeneous for radon and childhood leukemia. So one way we can improve this, and this is a study design that has come up in the recent, I would say, 10 to 15 years, is through register-based studies. So these are register-based case control studies where we don't require the participants to actively participate in the study, and we don't individually measure their exposure, but we use routine data to collect a large number of cases, but also a large number of controls, and then we use some indirect method of measuring individual exposures, such as by an exposure model, an exposure map. And these will be the studies, so these register-based studies will be the studies that I'm focusing on in this talk. If we, as I mentioned, most studies have been done on radon, and very few studies have actually been done on terrestrial radiation or cosmic radiation, and this summarizes the ecologic studies and the case control studies that have been done on this topic. And as you see, the picture here is also more heterogeneous. And, but let me now turn to individual studies. So the largest register-based case control study that has looked at both radon and natural and terrestrial gamma radiation was this study from the UK that was published in 2013. It's a very large study. It included over 9,000 cases and 11,000 and about 12,000 controls. These controls were taken from birth records, so the investigators knew where these children lived at birth. So they also were able to assess exposure at birth. And they assessed radon exposure using a map, a predictive map based on many measurements done throughout the country, which had quite a high resolution. The gamma radiation, unfortunately, was measured at a district level. So they took the average dose that people received in a district. The results of this study were quite interesting. So here you see a dose response for cumulative dose of gamma. So I also must mention this, the dose they looked at was cumulative dose, so they had to make the assumption that the children didn't move since birth. They had stayed at the same location. If you assume this, you can calculate a cumulative dose that they received. And here you see the cumulative dose on this axis, and then an estimation of the dose response. And if you assume a linear dose response, they estimated about a 9% increase per milligray gamma. Now that translates to about an excess relative risk per sievert, or per gray, of about 90. So this is in the range that we would expect from the lifespan study. It's a very high value, but it's in that range. There are very wide confidence intervals, so the confidence interval goes from 2 to 17%. This is for terrestrial radiation. They didn't find anything for radon. And they didn't find anything for the other childhood cancer tumors like brain tumors. The results were not significant. So we did a similar study. We also did a register-based study in Switzerland, but this was a cohort study, and I will quickly, briefly explain what the difference is. So in our study, we actually included the entire Swiss population of children under 16 years old, and we had data on this from the national censuses in 1990 and 2000. So we were able to include about 2.1 million children. And the cases that arose in this population we identified through the Swiss Childhood Cancer Registry, which is a national registry of all the children that get cancer. So exposure was assessed. We know where all these 2 million children live at the time of census. We have precise geocoded place of residence. And so we can assess exposure at the time of the census, and then we can follow up these children until they either get diagnosed with cancer, or they die, or they migrate away from Switzerland, because if they go away from Switzerland, we won't be able to register them anymore, or until they go out of childhood, their 16th birthday. So we can measure how many cases occur over these person years lived through childhood. This is a picture of the study design. So you have the census population in 1990 and 2000, and these are linked individually with each other. And we've also linked them with immigration statistics, so we know the people going out and the people coming in, and with deaths. And importantly, we have linked in the Swiss Childhood Cancer Registry, so we know which of these children actually developed cancer. Here's a graph just showing you how the children in the Swiss Childhood Cancer Study, which of the children that we could include. You see that we have about 3,500 patients that were diagnosed in the period from 1990 and till 2008. That's the period that we have follow-up on. Of these children, we found that about 2,000 would have been alive and living in Switzerland and still healthy at the time of the censuses. And of these, we were able to link about 1,700 or 1,800 childhood cancers. So if you compare to the English study, these are all cancers. So of leukemia, there would be about a third of these cases. So it's a much smaller study than the UK study. So how did we assess exposure? This is a map a model we used to assess exposure to radon. It's a model based on over 44,000 measurements made throughout the country in houses in Switzerland. And we used a regression model that includes soil texture, tectonic units, housing type, urbanization, the floor of the flat, and the year when the building was constructed. And we tried to validate this model to see how well it predicted the dose in houses that weren't used in the model, in new measurements. And the association wasn't very strong, so there was only about 20% of the variation explained by the model. But nevertheless, it's the best model we have, and so we used this to calculate exposure to radon. We then had a different model for terrestrial gamma radiation, which was based on a large set of measurements made throughout the country. So this was some measurements made directly at the site, some laboratory measurements made from soil samples, but also airborne measurements. And we had about one measurement per 25 square kilometers. So from these measurements, through the interpolation of these measurements, we used a map created by Riebach and colleagues. This radiation map here consists of several components. The first component is cosmic radiation, and this is mainly just a function of the altitude. And in Switzerland, we have the Alps that pass through here. So the higher locations here, of course, have a higher dose. Then you have the terrestrial gamma radiation, which is mainly also as a function of the rock uranium content in the rocks, which is also higher in the alpine areas. This is the major component of our background radiation of this map here. And then we have a small component here, yet mainly in the south. We saw some of this in the talk yesterday, that comes from that is fallout from the Chernobyl accident and is mainly due to cesium isotopes deposited here in this area. So this is, if you sum all these components, you get to this map, and this is what we used to estimate background radiation from cosmic and terrestrial sources. So let me now turn to the results. These are results that we published for radon and childhood cancers, and I'm showing you the results for leukemia only. You see here the different categories of exposure, so a low exposure and high exposure, and we also estimated a trend per 100 becquerel per cubic meter. So you see here, and it's much easier to see here in the graphs, that we found very little variation of the risk with over these different categories. So this is a hazard ratio, and let me briefly explain. A hazard ratio is similar to a risk ratio, is what we use typically what we use in a cohort study. But for rare diseases, you can simply assume that this is a risk ratio. It has the same meaning. So we don't see any results, any association with radon in our study. The picture was a bit different when we looked at gamma radiation and cosmic radiation. So this is the total dose from gamma and cosmic radiation. And here again are different categories. So under 100 nanosievert per hour, and the highest category being over 200 nanosievert. So this is an hourly dose rate. And over 1 year, this amounts to perhaps in this category, approximately 2 millisievert per year. So we have very few cases that occurred in this highest dose category, but the risk ratio or the hazard rate was highest in this category with a doubling of the risk. If you look at this as in a dose response manner, we also fitted a linear trend, and you see that we estimate an increase of about, we have a hazard ratio per 100 nanosievert per hour of about 1.25, which is non-significant. And it's mainly due to, the increase is mainly due to this last category here. So we also wanted to do an analysis that we could compare with the UK study by calculating a dose response with cumulative dose. And here we again had to make the assumption that children lived at the same place that they lived at census since birth. So if we assume this, we can again calculate a cumulative dose from terrestrial gamma and cosmic radiation. And these are the results we get. And I show here only the results for leukemia and acute lymphoblastic leukemia, which is the most important subtype of leukemia in children. And you see that we estimate about a 4% increase per millisievert dose with quite wide confidence intervals here. And in fact, we found a very similar number of 4% for brain tumors too. When we looked at the sub-cohort of children that had a stable place of residence that had not moved over at least 5 years before the census, so these are children for which we think the assumption that they stayed at the same location holds since birth is better and our exposure measurement is better. Here we in fact see stronger effects which are almost significant at the 5% significance level. So if we compare our results to the English study, we see very similar and compatible results. So we observed for leukemia in the Swiss study about a 5% increase per millisievert, 5% increased risk with confidence intervals from 0 to 10, and in the UK study it was 9% with confidence intervals from 2 to 17. So our results are very compatible, and they're also comparable with what we know from the lifespan study. We were quite surprised that we had quite narrow, similarly wide confidence intervals, although our study was much smaller. We would have expected much wider confidence intervals in our study. And we think the reason is that we had, first of all, a cohort study, which is statistically more powerful than a case control study. We also had a wider range of exposure due to the Alps in Switzerland. And the UK study, as I mentioned, had quite a poor spatial resolution of the exposure. Now, so to sum up these two studies, we see that we see actually what we expect. We find little effects for radon. We find quite strong effects, as we would expect from the lifespan study, for terrestrial gamma and cosmic radiation. And we find it mainly for leukemia. So if these had been the only studies to date, I would have ended on that note. But since in this year, actually, 2 studies appeared, one from Finland and France, and I briefly want to spend just 2 slides on them because they are not entirely compatible. So the first study from Finland was also a fairly large study which had included 1,000 cases of leukemia, childhood leukemia, and 3,300 controls. And they only looked at terrestrial gamma radiation. And the good thing about this study is that they had the full residential history of where these children lived since birth, so they could properly calculate cumulative dose. So in this study, they did not find any increased risk with cumulative dose, except in a small subgroup here of cancers that occurred under the age of, or between the age of 2 and 7. So there they had a significantly increased risk. And also in a subtype, in a genetic subtype of cancers. This is the French study. This is also a very large study, similar in size to the UK study. So they had they did two different types of study. One was an incidence study. You can think of this as an ecological study, but with a very small area unit. So it's quite a precise study. The area units were very small and scattered, and so they had 36,000 municipalities over all of France. So you can imagine that we have quite a high resolution with this kind of study design. They also did a case control study with 2,700 leukemia cases and 30,000 controls. They had a much higher resolution of exposure both for radon and terrestrial gamma than the UK study. So their spatial resolution of these measurements were at a scale of 1 times 1 kilometers. And their exposure was assessed at diagnosis rather than at birth. So if we look at the results from this study, we see these are the different categories of exposure, and we see very little variation in the risk over these categories. And if you do, this is in standardized incidence ratio, again, you can interpret this as a relative risk. So this is from the incidence study, and if you look at the standardized incidence ratio by millisievert, you see basically no effect, with a very narrow confidence interval of 0.99 to 1.1. So this study is a bit contrary to all the other findings that the other register-based studies. So let me come to a conclusion, and I wrote these conclusions actually before I had the results of these two newer studies, so I've just added some things here and there. So overall, the evidence from the ecological and conventional case control studies is inconclusive. But more recently, the register-based case control studies and our cohort study suggest that background radiation does contribute to the risk of childhood leukemia, with the big exception of the French study that I just showed you. The excess risks are compatible with risk models that are developed from the atomic bomb survivors and do support the greater susceptibility of children to radiation-induced leukemia, also at low doses, again with the exception of France. So I believe that we still need further studies, and the main challenge here is to obtain accurate exposure measurements on a large scale and on large representative samples. And I think this remains the greatest challenge for this kind of research. So we need more large studies, and I think one way we could do this is maybe to start pooling or to start working together between different countries to make one large study that would have better power to actually look at the effects of low-dose radiation in children. And with that, I'd like to close and thank you for your attention.